In a senior system design interview, you might be asked to architect an object storage service similar to Amazon S3. The prompt usually sets a target capacity of 100 petabytes of data. To understand the complexity here, we have to look past the top-line number. 100 petabytes is a physical logistics problem involving the constant, inevitable failure of millions of spinning magnetic hard drives. A junior engineer might attempt to solve this by slapping a standard POSIX file system onto a giant disk, hoping that server procurement can simply replace the hardware fast enough when it burns down. That approach immediately violates the strict constraints of the prompt. At this scale, the system must guarantee 6 nines of durability, that's 99.9999%, and 4 nines of service availability. Furthermore, standard hierarchical file structures, directories nested inside directories, completely break down. Searching through complex folder trees to locate a specific file requires multiple disk reads, creating fatal I/O bottlenecks. These bottlenecks force us to rethink the very nature of storage, moving away from local disk management toward a more distributed architecture. The core architectural flaw with standard file systems is proximity. They store the file's metadata, names, sizes, and permissions, physically right next to the heavy payload data on the disk. Modern object storage borrows from the Unix inode philosophy. The map detailing where the data lives is stored completely separately from the actual raw bytes. In this diagram, API servers split incoming requests. A lightweight metadata path points left, a heavy data path right. The server queries the metadata DB for a UUID, a direct coordinate locating raw bytes inside the file storage plane. The cynical reality of this design is that you have to build a highly optimized, heavily sharded NoSQL database strictly to remember where you put the actual files. This decoupling allows the data plane to expand horizontally across generic hardware, while the metadata layer handles the complex indexing required for high availability. If a user attempts to upload a single continuous 10 gigabyte file over a standard TCP connection, a microscopic network blip will sever the transfer, resetting the entire upload to 0. Forcing users to restart massive uploads from scratch because of routine internet latency is unacceptable for system performance and destroys user trust. The engineering solution is the multi-part upload. The client application mathematically slices the 10 gigabyte file into dozens of smaller, independent chunks, transmitting them in parallel. This provides aggressive network resilience. If one 10 megabyte chunk fails to upload, the system only retries that specific chunk. The rest of the payload is completely unaffected. On the back end, the metadata database tracks the exact UUIDs of each individual chunk, holding them in a pending state until every piece arrives and the object is reassembled. A large file does not physically exist in transit. It is a logical illusion, maintained by the metadata store's tracking of parallelized chunks to protect the system from the realities of the internet. 6 nines of durability means you are statistically allowed to lose exactly one object out of a million per year. Because hard drives are constantly in the process of failing, aggressive replication is the only viable defense against hardware failure. This diagram shows replication strategies. Same region protects against rack failures. Cross-region protects against data center disasters. The trade-off is cost. Replicating 3 times means 100 petabytes of data requires 300 petabytes of physical iron. You also have to defend against bit rot, silent data corruption occurring on magnetic disks over time. The replicas must constantly verify cryptographic checksums against each other to detect and self-heal these anomalies. We achieve 6 nines of durability by treating hardware as a disposable commodity, using software to constantly copy data away from failing components before they crash. Saving data in a distributed system is highly optimized and relatively simple. Actually deleting it is a distributed nightmare. Object storage strictly follows a write once, read many model. Because files are heavily replicated across different geographic regions, performing an update or delete operation in place is impossible without causing massive locking delays. Deleting an object simply writes a digital tombstone marker into the metadata database. This instantly hides the object from the user, but the physical bytes continue to sit on the disks, quietly racking up storage costs. To reclaim space, you must introduce a garbage collector. This background process endlessly hunts down tombstoned files across thousands of servers to physically remove them. The final required step is compaction. Ripping out deleted files leaves empty holes in the disk blocks, which ruins read performance. The system must append the remaining active objects into a single, dense new file, and then erase the old ones. True deletion is an incredibly expensive, deferred maintenance task. It is strictly necessary to prevent the system's own immutability rules from causing massive storage bloat. In the context of the system design interview, the interviewer is waiting to see how you balance these competing architectural forces. You have to detail the trade-off between latency and consistency. Waiting for all 3 cross-region replicas to acknowledge a write ensures strict consistency, but it creates terrible latency. Eventual consistency dictates that a write is acknowledged quickly, creating a brief window where a user in region A might see a different file version than a user in region B until the background replication catches up. You must clearly articulate the core mechanisms: the heavily sharded metadata database, the parallel transmission of multi-part chunks, and the aggressive asynchronous garbage collection. Acknowledging the brutal realities of network drops, disk fires, and ghost data is exactly what separates a theoretical textbook answer from a strong higher evaluation. A 100 petabyte system succeeds or fails based on the management of continuous data degradation, replication schedules, and the physical lifecycle of the underlying disks.